Today we'll use the rules of probability to answer questions and find the sample space of an event. So we're going to start off with a little birthday example. We're going to assume birthdays are equally likely, and suppose we have 18 students. Assuming that there are 365 birthdays, what is the probability of 18 different birthdays? So take a moment and think about it. Well, the first person obviously has 365 days out of the year to have their birthday. Well, the next person, if we're assuming everyone has a different birthday, there's only 364 days left in the calendar. And then the third person would only have 363 days left in the calendar. And we would continue to count backwards until we get to 348, which is the 18th day into the year. And we would divide that by 365 to the 18th power, which are total possibilities. And we do get a probability of about 65%. Now if we assume birthdays are equally likely, suppose we have 28 students. Assuming there are still 365 birthdays, what is the probability of 28 different birthdays? So do you think the probability will increase or will it decrease? The probability will actually decrease because if you look at our we're going to start at the 365 and we're going to count backwards 28 days to about 338 and divide by 365 to the 28th power. And it is going to be a smaller percentage. A random phenomenon is a situation in which we know what outcomes could happen, but we don't know for certain which particular outcome will definitely happen. A trial, if you recall, is one observance of a random phenomenon, and an outcome is the result of that one trial. Okay, so similar to when we talked about simulations. An event is a collection of outcomes that satisfy a given condition. The collection of all possible outcomes of a random event is what is known as the sample space. I didn't even know I could do that. Okay. So some examples, a score on a test, okay? In this case, we're assuming percentages, and this is actually incorrect. We technically should write it differently. We should write it as S equals, squiggly bracket, 0, 1, 2, dot, 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 100%. Okay, if you do the 0 dash 100%, probably not the wisest choice. If we look at rolling a die, those are just numbers 1 through 6. A coin toss would just be heads or tails. And free throws made in a 2-shot try, that would be 0, 1, or 2. This brings us to the law of large numbers, and all it states that in the long run, the frequency of outcomes approaches a single value, meaning it's the probability of the event. So notice that we have a graphic here, and we're looking at the number of coin tosses and the proportion of heads. Obviously, this first coin toss was a head because we had a 100% likelihood of doing so. But as we notice, as the number of coin tosses increases, that probability eventually is about 50%. When we discuss the law of averages, we're saying after a long run, if an outcome has not occurred, it is due to occur. Well, this actually does not exist. Next, we're ready to talk about probability rules. Remember, probability is a number between 0 and 1. It is never negative. It is never larger than 1. For some event A, it is always between 0 and 1, including 0 and 1. If I take the set of all outcomes, it has a probability of 1, meaning I would take all of the outcomes in the distribution, add them together. It should equal 1 whole or 100%. Meaning for our sample space, if I were to add all those probabilities together, we should get 100%. These two things make up what's known as a legitimate probability distribution. So you might see something where it'll say verify that the probability distribution is legitimate. So you would take your probability of the first event plus the probability of the second event and the third, etc., to show that it equals 100%. And the probability of an event A not occurring is 100% minus the probability it does occur, because it's everything left over. When we start talking about theoretical probability, this is a mathematical model demonstrating the outcomes of events. Remember, probability is the ratio of desired outcomes to total outcomes. And notice we might see things with decks of cards, we could have 2 die, we could have coin flips, and we could have colors on a spinner, multiple ways to find theoretical probability. So now we're just going to look at some simple examples. We're not going to do that first bullet because obviously we aren't in the classroom, right? Finding the probability of choosing a male in this room. If we wanted to find the probability of rolling a 4 on a single die, that's just 1/6, or approximately 17%. To find the probability of rolling at least a 4 on a single die, sometimes it helps if you write out the sample space because it gives you a visual. Okay, so if I know the outcomes on a face of a die is 1 through 6, if I see this word at least 4, well, what does that mean? Well, hopefully you'll identify it. At least 4 means 4 or higher. So how many numbers are 4 or higher? 3. How many total outcomes? 6. So 1/2. And then find the probability of drawing a face card from a deck of cards. Okay, so a face card. Cards that have faces would be your jack, your queen, and your king. Remember, there are 4 of each type. 4 times 3 is 12. So we would take 12 out of 52, or approximately 23%. Yay, we made it to the end. It's time for practice. The end.